Hello students, today we are going to start a new chapter. The next one is solid semiconductor and electronics involved in it. So in this chapter at first we will learn that how there is a shift from the pure hydrogens theory given by Bohr, how we vary from this theory when we talk about a crystalline structure. Actually, when Bohr gave this theory for hydrogen atom, he was considering the fact that hydrogen atoms are isolated from each other and they hardly affect the neighboring atom. But in crystalline form, what happens, the atoms are closely placed and their nucleus comes close to the valence electrons of the neighboring atoms, and thereby the allowed energy levels for those valence electrons are appreciably modified under the influence of neighboring nuclei of the atoms. However, this modification is not so significant when we consider the core electrons. So here we are taking the example of a silicon crystal. In this, on the right hand side, we have mention the allowed energy level given by Bohr's theory for a hydrogen atom, and then we also see that these are the core electrons given in 1s2 suborbitals, 2s2 and 2p6. These are the core electrons, but there are 2 electrons in 3s2 suborbit and 2 electron in 3p orbit, and therefore there are 4 electrons in the valence and others are in the core. Other electrons are the core electrons. So these 4 are the valence electrons. They have a definite allowed energy level corresponding to the allowed orbit, and when we imagine a situation that there is a large gap between this type of energy distribution in the orbital energy levels are in accordance to the Bohr's theory. But when we talk about the actual separation of the atoms in case of silicon crystal, as this separation is reduced, the allowed orbits, allowed energy levels increases more than what was predicted by Bohr's theory of hydrogen atom. And these allowed energy levels are very closely spaced. As the separation is reduced, the allowed energy levels increases manifold. And since they are very closely placed allowed orbits, therefore we call it allowed energy levels are very closely spaced, therefore we call it a band. And the gap between, when we consider the actual separation between the atoms of a silicon crystal, while it is forming the crystal, the atoms are placed in a fixed location, and in that situation the distance between the valence band where the electrons actually resides and the electrons which becomes conducting when it is gaining some energy from some thermal source or by some another means and jumps into a higher orbit of greater energy, that is called conduction band. So the gap between the conduction band where the electron starts conducting or capable to become a free electron, and the gap between these two is known as energy band gap. And now overall we can say that there are 4 electrons in the valence band, and there is 0 number of electron in the conduction band at 0 Kelvin. But actually when we talk about the condition of room temperature, in that case some of the electrons may jump and go to the conduction band, and therefore some electric current flows when we apply some potential difference across the semiconductors. However, this flow is very low. So that's all for today. Thank you and have a nice day.